Now that we've had the opportunity to examine individual transformations on their own, we're going to put them all together in section 2.2.2 and graph the general sinusoid. Here's the definition. The graph of y equals a sine of b times x minus c plus d, or equivalently with the cosine wave, is a sine wave. Now remember, a sinusoid encompasses both the sine waves and the cosine waves, with amplitude absolute value of a. So the coefficient of the sine or cosine indicates the amplitude. Now, if that happens to be a negative number, that indicates that the wave has been reflected across the x-axis. But as far as measuring the amplitude, the height of the wave, we calculate the absolute value of that constant. If the argument is multiplied by a constant, b, then this creates either a horizontal expansion or compression, or specifically a change in the period of the sinusoid. To calculate the new period, we're going to take the original period of sine or cosine 2 pi and divide by that coefficient, and that yields the period of the transformed function. The phase shift is going to be described by this constant c. Now, the phase shift is tricky for two reasons. Number one, if that constant is positive, that means I'm subtracting a positive number. I'll see a negative right here. If I see that, the graph is going to shift to the right. However, if c is negative and I'm subtracting a negative, this sign is going to show up to be a positive. If I see a positive in that position, then we have a phase shift to the left. So the phase shift really goes the opposite direction as indicated by this sign. So number one, we have to be sensitive to the sign. Secondly, notice the format of the argument of our sinusoid. The coefficient b is outside this difference, x minus c. If it is not in that form, like example 3, for example, we definitely need to factor that coefficient out first before we can properly recognize the phase shift. And we will certainly practice that in an example. The final thing we're going to watch for is a constant outside the function, either added or subtracted to the sine wave. This represents a vertical shift, and this is very intuitive. If d is positive, the graph moves up. If d is negative, the graph moves down. So let's put all this information together and graph example 3. We want to graph one cycle of y equals 2 cosine of 2x plus pi plus 1. First of all, recognize that the cosine wave is multiplied by the constant 2. That indicates that the amplitude is 2. Also observe that's a positive number, so the orientation of the cosine wave will match the orientation of the original cosine wave. Remember, if that number were negative, then we would reflect that graph across the x-axis or invert the cosine wave. Now, to calculate the period, we need to determine this coefficient b. Notice again, the argument is not in factored form. So inside the argument, I'm going to promote those parentheses to brackets. I'm going to factor out the coefficient of x, whatever it may be, and in this case, it is 2. So I'm going to factor the 2 out from the argument, and that's going to cause this second number to be pi over 2. You can double check here. 2 times x is 2x. 2 times pi over 2 is pi. So in factored form, we can recognize that b is 2. So to calculate the period, we're going to take the original period of cosine, which is 2. We're going to divide by this coefficient, so the period is pi. This means in a length on the x-axis of pi, cosine will complete one fundamental cycle. Now that we have our cosine wave in factored form, then the argument is in the correct form to recognize the phase shift. The phase shift here is, notice it says plus pi over 2 in the argument, so the phase shift is the opposite, negative pi over 2. Or another way to say that is pi over 2 to the left. And easiest of all to recognize is the vertical shift. The vertical shift is the constant outside the function. We have a plus 1 here, so it's going to go 1 in the up direction. So we can record that as positive 1, or we can describe it up 1 unit. So with all of that information listed, we simply need to translate this onto our graph. I'm going to start with the concept of the vertical shift. So our original cosine wave, which is generally centered around the x-axis, is going to shift up 1 unit. So I can think of that as shifting that center line up 1 unit. Now for good measure here, I better label my y-axis. I'm going to do 1 tick mark per unit. Then I'm going to recognize that the entire graph has been shifted up 1 unit, so I can construct this dashed line as the new pseudo-axis for the cosine wave. Now, because the amplitude of this cosine wave is 2, we know that it's going to reach 2 units above that center line and 2 units below that center line. So at this point, we could even recognize the range as -1 to 3. And let's go ahead and fill in this domain. Domain doesn't change. It's always -infinity to infinity. Now, as you're learning this, if it is helpful, you can also put a horizontal for the maximum amplitude and a horizontal there for the minimum of your cosine wave. So we know that the cosine wave is going to be centered and fitted in between those green lines. Now, not only do we need to recognize that there's a change in the period here, but there's also a phase shift. So we need to figure out where that first fundamental cycle begins and ends. The easiest way to do this is to take the argument and trap it between the original period of cosine. So you can do the original argument or the one that we have in factored form. Either way will be just fine. So the original cosine wave will complete 1 fundamental cycle when its argument is between 0 and 2 pi. So we're taking the new argument here and trapping that in between 0 and 2 pi to figure out the beginning and end of the new period. Now I'm going to go through and divide each part by 2, all 3 parts of our inequality here. And then I'm going to subtract pi over 2 from all 3 parts. So we have -pi/2 on the left end, x is isolated in the middle, and pi minus pi/2 on the right end here is pi/2. So this means our cosine wave is going to start at -pi/2 and end at pi/2. Notice that the distance between these 2 points is pi, and the period of the cosine wave is pi. So let's go ahead and fill in our information. So at the leftmost end of this interval, cosine is going to reach its maximum. So I'm looking at x equals -pi/2. The maximum is going to be 2 units above that center line. At pi/2, x equals pi/2, cosine is going to finish its bowl shape again at that maximum point. Halfway in between those 2 points, cosine reaches its minimum. Halfway between the maximum and minimum, cosine crosses its center line. This is our new purple pseudo-axis. And halfway between the minimum and maximum, cosine again crosses that center line. So we have 1 fundamental cycle of cosine here. Now let's be very meticulous and label those 5 key points. So the final point here is pi/2 and 3. This point would be pi/4 and 1. This is the point 0, -1. We have -pi/4 and 1. And we have -pi/2 and 3. Now, to keep things in perspective, let's quickly sketch our basic cosine wave. Remember, the cosine wave begins at 1 and ends at 1. Halfway between, it hits its minimum. And halfway between the max and the min on either side, it has an x-intercept. So if we consider all of the different transformations that have occurred for our original cosine wave, we can see that it's been shifted to the left by pi/2 units. Notice here the distance between the beginning point of the green wave and the beginning point of the blue wave, that's a distance of pi/2. So it's been shifted left by pi/2 units. Also notice it has been moved up by 1 unit. It has been compressed to have a period of pi. 1 fundamental cycle now occurs in a distance of pi. And finally, it has an amplitude of 2, so it's a little taller than the original. So that's a lot of information to think about, but again, as you do your homework, go through the process that we've gone through so you can figure out what's the location of that first cycle. Let's go ahead and practice this again with a sine wave. On example 4, we're going to graph one cycle of y equals -2 sine of 2 pi x minus 2 pi minus 2. It's a lot of 2's. Let's recognize all of the components of this sine wave. First of all, notice it has a coefficient of -2. Now the amplitude, which is a distance, it's half the distance between the maximum and minimum, is +2. But what we're going to recognize is that because this constant is negative, this sine wave has been inverted or reflected across the x-axis. So I'm just going to make myself a note, reflect across the x-axis. So the original sine wave has an orientation looking something like this. So the one we're trying to graph is going to go the opposite way. Now, before we identify the period and phase shift, it's important to get the argument in the right form. We need to factor the coefficient of x out of that argument, staying in the argument, but as a coefficient. So we're going to factor a 2 pi off here. That's going to leave behind x minus 1, and then we have -2 outside the function. So the b, the coefficient of our argument here, is 2 pi. So to find the new period, I'm going to take the original period of sine, which is 2 pi, and divide by that coefficient b to get the new period. So in 1 unit on the x-axis, our sine wave will achieve 1 fundamental cycle. Also, looking at our factored argument, we can recognize the phase shift. Now notice we're subtracting 1, so our phase shift is +1. Or we can be specific and say 1 unit to the right. And finally, the constant out here by itself indicates the vertical shift. We can call that vertical shift -2, or we can simply say it's going to go down 2 units. To begin our graph, let's go ahead and label the scale on the y-axis. I'm going to use 1 tick mark per unit, and so we have integer values on our y-axis. Also, because the period is an integer, we can change the scale on our x-axis to reflect that. Now this is going to be a pretty compressed curve, so on the x-axis, I'm going to use every 2 tick marks for 1 unit. So the scale on the x-axis and the y-axis are a little bit different, which means our graph will be a little bit skewed. Now let's use the vertical shift to identify a pseudo-axis for this sine wave. So the relationship between the original sine wave and the x-axis will be transferred to this new blue shifted axis. Now, because the amplitude of this sine wave is 2, we know that this particular sine wave will reach 2 units above that blue axis and 2 units below that blue axis. So at this point, we could predict the range will be from -4 to 0, and the domain is always -infinity to infinity. Now, let's determine where that first fundamental cycle is located. Recall that for an original sine wave, as the argument ranges between 0 and 2 pi, we get 1 fundamental cycle. So I'm going to take the argument of this sine wave and trap it in between 0 and 2 pi. Now, you can do the argument in factored form or the argument in its original form. Either way is going to be fine. So I'm going to add 2 pi all the way across this inequality. And then I'm going to divide everything by 2 pi. So we end up with 1 less than or equal to x less than or equal to 2. So our first fundamental cycle is going to range between x equals 1 and x equals 2. So remember, our original sine wave has 5 key points. For this particular graph, we're thinking about reflecting it across that axis. So we're going to mimic that pattern with this new information. So at the beginning and end of the period, the sine wave is on its axis. So at x equals 1 and x equals 2, the sine wave is on the axis. Halfway in between, the sine wave crosses its axis. Now, halfway in between those intercepts, this particular sine wave is going to reach its minimum. So halfway in between here, sine reaches its minimum, and halfway in between the other 2 points, sine reaches its maximum. So we have one fundamental cycle of the sine wave. Now, let's be diligent and label those points. The rightmost point is location 2, -2. The center point here is located at 1 1/2, or we'll label it 3/2, -2. And the original point, 1, -2. This minimum point, notice it's 1 1/4, or we'll call it 5/4, -4. And this maximum point, 1 3/4, or 7/4 and 0. Now, I'm simply using the scale that we listed there to locate those points, but don't forget you can also calculate those. For example, to find the location of this point, specifically the x value, I know it's going to be halfway in between the x value of these 2 points. So if I find the midpoint between those 2 points, 1/2 of the sum, 3/2 plus 2, that'd be 1/2 times 7/2, we'd end up with 7/4, which is what we have reflected up here. So be very diligent in labeling your points. Label your scale very clearly, but also remember you can calculate the location of those points using midpoints. So in this section, we looked at sine waves that exhibit all of the transformations, reflections, change in amplitude, period, phase shift, and vertical shift. Every single one of those aspects can be used to model something in real life. So in the next section, we'll talk about some applications.